I'm going to start by explaining the situation we found ourselves in about a year and a half ago, right? So a few years ago, the business unit that I work with in Chevron, let me see if I can get this to work. Yeah. So the business unit that I'm a part of in Chevron, I'm part of the unconventional. The BU that I'm part of, we decided to take a factory approach to drilling and completing wells, drilling, fracking, and completing wells, right? So for the non-oil and gas folks in here, just visualize a factory where you produce electronic widgets, right? And you have multiple stages of the factory. The first stage may be, building your PCB. The second stage may be putting your components in there, and then finally building the product, right? So I have not included all the stages of the factory here, but the two biggest ones. So we have several what we call rig lines. These are drilling rigs, and each rig basically has a schedule of pads. Now, pads are nothing but a grouping of wells. You can have 4, 6, 8 wells per pad. So each rig is going to basically drill a set number of pads in any given year, right? And after drilling is complete on that drilling rig, it goes into a virtual queue of what we call the drilled but uncompleted wells queue, right? Now, the next stage beyond this, and like I said, I've not included some of the stages between these two processes, but the next stage for us is to essentially frack and complete the well, right? So you can see that there's not a one-to-one relationship between the drilling rig and the number of fracking resources, and there's a reason for that. Fracking is actually a very expensive operation, right? And so we wanted to manage the amount of fracking resources we had on our schedule, because we wanted to manage our cost exposure, obviously, and to also manage the amount of inventory that we were carrying at any given point in time, right? So the problem that we were asked to look at, and it was interesting the way the problem was first asked of us was, do we have enough wells in the drilled but uncompleted inventory to keep our frac crews optimally utilized? Okay, that was the question that was posed to us. I kind of pushed back, and we ended up reframing the problem. And after several meetings back and forth, we came to the conclusion that the problem really was not if we had enough inventory, but also if we had enough crews to service the inventory that we had, right? And so the problem in reality was, what was the ideal number of resources we need to allocate to our fracking portfolio? And most importantly, when do we allocate those resources, right? So at what time do we bring those resources online so as to maximize or optimize the portfolio value, right? So if you're looking at a 3-year portfolio of wells, how much resources do we allocate? When do we allocate them to optimize portfolio value, right? And digging deeper, what happened was we found out that there were actually two functions that were taking us in opposite directions, right? So this actually ended up being a classic OR problem. And luckily, I have a background in OR, so my team leader and I kind of dug this through and said, this is not a classical DA problem. This is more of an OR problem, and we need to leverage optimization techniques to address the solution space for this particular problem, right? So with any system, there are going to be constraints, and so we were operating under multiple constraints. I'm not going to go through the entire list, but some of the key constraints were our drilling times had a large degree of uncertainty, right? Correspondingly, our fracking time had a large degree of uncertainty. We had to look at frac crew efficiency. We also had to look at cases where certain wells in certain areas could only be fracked and completed by a crew that was certified for that area. So that kind of posed an interesting constraint. We also had a situation where if you were basically drilling in one area, you couldn't do any fracking within a mile's radius of it. So that posed a very, very challenging constraint for us, right? So we had to model the optimization scenarios given all these constraints, okay? Sorry. So why OR? So one of the things I mentioned was when we kind of dug into this problem, there were two opposing functions, right? We call them objective functions in the OR world. One was that if you tried to increase the number of crews, you would service your inventory much faster, right? If you reduce the number of crews, you would start basically deferring the production of those widgets, so you started losing revenue. You basically had deferred revenue, right? So if you had a schedule where you had the widgets come online at a certain point in time, but because you didn't have enough crews to produce those widgets, you would basically start deferring production, and as a result of which, you started losing revenue, right? So this ended up being a convex optimization problem, and I have a chart which explains what convex optimization is. But this was not a classic DA problem, right? So we went back to kind of looking at OR as a possible solution space to this. So there's the informed definition of OR. OR is the application of scientific and mathematical methods to the study and analysis of problems involving complex systems, right? That's just the classic informed definition. For anyone with an OR background, there are several approaches that are kind of well accepted within the OR world. You have LP, which is linear programming. You have queuing theory, which is what we use for this particular solution set. There is network modeling, there's nonlinear programming, and so on and so forth, right? So I'm going to go to the next one. I think, Billy, you're up. Okay.
Thanks, Bobby. I need the click.
Sure.
Thank you. Yeah, so Bobby had talked to me about giving this talk, and I thought that it might just be good to talk about kind of the background and context of operations research and management science. And Bobby said, well, if we're going to talk about the context and the history, well, then you got to do it. So that tells me I'm really the old guy. So I guess I met that criteria. So can I just ask how many people here, and we'll do it the old-fashioned way, just show of hands. When I talk about operations research management science, you feel like you know what that is and are comfortable with those terms? Okay, so I'm probably preaching to the choir to quite a few of you. But I do think when folks are new to come into DAG and decision analysis, it's kind of good to understand the context and how it fits together. So he just asked me to give a little bit of the history, and then he'll get back to the problem we were solving. So this is a picture out of, or a snap out of Newsweek from July 26, 1954. And it's the science column that was in there, and it introduces the traveling salesman problem. So if you, probably many of you have heard of that, but that's just, the issue is if you have a list of locations and you want to minimize your travel, could be time, could be distance, usually I guess distance is typically what's used, how can you go between each place without returning to a city or the locations and make a complete circuit? And this actually can be a very tough problem to solve at times. And in terms of mathematical computation, it can get quite complex. So let me just blow up the little blue box there. The quote there, by an ingenious application of linear programming, a mathematical tool recently used to solve production scheduling problems, it took only a few weeks for the California experts to calculate by hand the shortest route. Those people were at RAND, that's who did the study, right? Well, I mean, obviously the world has changed a lot. This is just one example. You can go to a website and just with a few clicks, it'll give you the optimum route between them. So computing power has really allowed us to do things that were really, really hard to do before. By the way, just a good friend of mine works at UPS, and when they have those, when the drivers come up and they have a tablet device with them, right? Everything gets scanned onto the truck, and it's got everything on there. Well, I guess it was probably about 15 years ago when they started to embed an optimizer into the tablet, and I don't know the exact year, but it was about that. And so they were at the, they rolled out a prototype, and he said, I knew it was going to be successful when I heard the loading dock manager telling a driver, hey, you need to get out of here, you need to get going. And he goes, wait, I'm not done optimizing, and he knew when the driver wanted to run the optimizers, then he knew that, hey, it works. So they've gone through, I think, at least three versions of what they give out in the tablet. And, as we know, electronics get smaller. We all have more capable things on our wrists and in our pockets, right? So they made them smaller. The big feedback he got from the drivers was, you made the tablet too small. And when he asked why, that was a common feedback comment. Well, if a dog comes up to me, I need to be able to fend it off. So it just gets back to really framing well and understanding your objectives of what you're trying to do. So I just made this graphic to kind of talk about the trends. A couple people yesterday mentioned generals fighting the last war. I'm a retired Army officer, and that's known as victory disease in military theory. Very often a country that won the last war loses the first battle and the next one. That's very common. And what happened in World War II in England is when Germany invaded France and they had the evacuation through Dunkirk, right? They had the reverse of victory disease in the United Kingdom because they were really worried about surviving. So they were ready to embrace any resources to help them. They actually assembled a bunch of professors, and they found that these operation research techniques, there they call them operational research, were really, really helpful. So there were a number of, everything in military theory is measure, countermeasure, countermeasure, type of thing. But they really had great step increases in the ability to extend operations, like searching for U-boats in the Atlantic campaign and that type of thing through the use of these mathematical tools that were developed. And so I think the first OR book was Search and Screening by Morse and Kimball. It was published after the war. As I recall, they were in the U.S. Navy Operational Research Department. And so I just started this timeline starting after World War II in 1945. What happened is industrial engineering and system engineering too, to a degree, took this OR toolkit, and when I say OR, sometimes management science, I use those terms interchangeably, but they brought them back and applied them, initially a lot of industrial engineering. There's a big resurgence of manufacturing in the United States post-World War II, and they used those techniques to refine and do a better job to produce and be more efficient in the production and so on. So I just tried to indicate on here, and this is just my attempt to tell the story, is that initially they were applied to very cyclic-like decisions. If you think of the frequentist view, if you're making light bulbs, whatever you're making, well, what's the sample size they need to get a certain confidence in quality and so on, and just a very repetitive type of thing for quality testing. But eventually there was a migration to the idea of how does this get applied in the boardroom? Like if in a company, if you're going to do an entry into another country with your company, well, you only want to do that once, right? If you're doing it a second time, it means the first time didn't go well. And that's when decision analysis evolved. So all the tools like simulation, optimization, stochastic methods, and so on evolved earlier, and DA was really the capstone state in terms of the evolution, at least in my view, of the OR family of tools. And you've heard people talk about frequentist and Bayesian. We kind of did that migration too as well. So people alluded to how it used to be that if you were a Bayesian, that was a black mark against you. So I guess I'd really like to just say for the value of OR is that in my mind, when you're structuring a DA problem and you look at what goes on the end of the branches of the tree, sometimes there are good tools to turn to fill out, to understand what data goes on the end of each of those branches. And it may not be something that's a standard DA tool to get that information. And for me, an analogy in the upstream part of oil and gas, we always turn to the subsurface teams that do simulation work, and they do reservoir simulation and do quite a bit of work to do a good job at that. And then they hand it to the decision analyst, but I think the decision analyst normally doesn't think about that. So you may need to go to other folks for different types of problems. And with that, I'll turn it back to Bobby. Thank you.
Okay. So as I mentioned, we used queuing theory to solve this particular problem. So the best analog I can give is that of a supermarket, right? So imagine you have all these customers walking into a supermarket. One of the challenges for the supermarket manager is to keep the right number of cashiers, open up the right number of cashier lanes at the right time, so the customers don't have to wait, right? The difference here in our oil and gas world is that the customers are the drilled wells, the cashiers are the fracking crews, right? So in a supermarket, the customer doesn't mind waiting a little more. In our world, if a drilled pad is actually waiting for a while, you're actually losing revenue. So there is an incentive for us to not keep the drilled pad but uncompleted pad in the DUC inventory for longer than necessary, right? So in using queuing theory, what we basically decided to do was to use we had several options. One was I looked at commercial optimizers, but commercial optimizers are expensive. Number one, right? So the best approach I could take was to develop my own algorithm to deploy this solution to this particular problem. And as I mentioned, this turned out to be a convex optimization problem, right? So the red dot you see here, so on the y-axis, you have the portfolio value loss. So that's the amount of value we are leaving on the table by not completing the wells on time and putting them on production as per the schedule. On the x-axis, that's the number of fracking crews that we had the choice to deploy, right, given any point in time. So the red dot that you're seeing out there, that was the initial estimate of the number of crews that we needed, right? And you can see from this parabola that if we decided to keep those many number of crews, that's the amount of value loss we would have basically left on the table, right? So in comes this algorithm that we wrote, and the algorithm actually said, you know what, you need to hire more crews, because by hiring more crews, even after the money you spend in hiring the more crews, you actually are leveraging a lot of the value loss. You're moving the revenue forward and capturing that deferred revenue, which more than pays for the amount of, for the amount that you're spending behind the crews, right? What was also interesting is that the point on the right portion of the curve, that's when you start increasing the number of crews beyond the optimal, you start eroding portfolio value, right? So there is a balance point, which is right at the base of the parabola. So this is similar to what we call gradient descent in data science. So that base of the parabola is kind of the ideal point, the ideal number of crews and when to hire them. That gives you the best portfolio value, given all the constraints that we were trying to model, okay? Now, the entire model was actually written in Python. The front-end interface, and this is for the technical geeks in all of us, the front-end interface was just a simple XLDA model. The computational algorithm, like I said, was written in Python. I had to make a choice in basically creating mathematical formulations for my constraints or deploying them programmatically. So I went the programmatic route. So this is kind of a fit-for-purpose algorithm specifically for this problem. And for a 3-year portfolio of pads, the algorithm basically runs a random number of simulations for drilling uncertainties, fracking uncertainties, crew efficiencies, what we call different constraints. So, for example, how many wells are likely to get deferred because of, SIMOP constraints or, operational constraints and so on and so forth. So over a period of time, we tested this algorithm for stability and for the results. And some of the results were intuitive. Some we had to scratch our heads to make sure that it was telling us the right thing, right? But it did. So long story short, the algorithm basically ran around 25,000 simulations with full probabilistic complexity. And I'm still running this on my laptop, so it takes about 5 to 6 minutes on a laptop. To date, I think I've run close to 3 million simulations. These are basically 3 million different portfolios that I've built. And the algorithm has been very, very stable, right? So that's the technical summary in a nutshell. I think we have 30 seconds for the last slide, Bill, which is talking about why the kind of the cross-functional thing between OR and DA as to why we need to blend these things together.
Oh, well, I mean, I think the point here was just, I think really I made it before, is that we want to apply the best tools to get the best decision quality, and it's really a blend of those things. So this was just to illustrate the point that you can bring different techniques to bear here, and I really think the idea of framing and then the decision tree, and if you think at the end of those branches, is that what is it you need to know at the end of each of those branches, and what's the best way to get that information? And so it may be something that is easy to do for you, in which case, it's easy to get. A lot of times, though, there'll be technical information, and you need to get other folks, and it'll involve other techniques to do it.
Thank you.
So I see one clarification question here. Did you assume that other decisions were given, e.g. number of rigs?
So that's a great question. So, and Bill, you can take up on this, but my experience was, and this was kind of a flaw in our approach, I'll be very honest about it, is when we looked at this entire factory, when we look at any factory, it is a system of systems, okay? Because a system, a complex system has component subsystems in it, right? From the OR perspective, I would rather model the entire system, because to me, oftentimes when you deploy optimization, the whole is often greater than the sum of the parts, right? In this case, all we really modeled was the fracking portion of the factory, right? Because that was the more immediate problem on hand. Now, we are still talking about looking at all the stages of the factory and applying OR to the entire factory as a whole, because we feel that given multiple stages of the factory, inefficiencies with one part of the factory can manifest themselves in interesting ways in other parts of the factory, both backwards and forwards, right? I don't know if that clarifies your question. Yes?
Did you consider the implications of replicating this factory approach throughout your portfolio? And if so, what were those implications? In other words, if deploying more resources makes sense for one individual area, given the vast area that you all have under ownership or lease, in some areas, particularly the United States, that are,
Right.
where you'd be doing this. What are the implications for the aggregate portfolio, and then
Okay.
the aggregate, the implications not only for the portfolio but for the enterprise as well?
So that's a great question. What we actually found out when we ran different distributions for drilling, fracking, et cetera, was that the obvious answer was not to add more resources in some case, right? That was the intuitive answer. So for example, if drilling slowed down, you had inventory build up at a slower level, so you don't need to add more fracking resources. On the contrary, if drilling sped up, you had more wells being dumped into inventory, so you need to get more resources. But there were some problems on the cusp, some distributions on the cusp where we saw that improved efficiency in drilling, right, was still telling us to get the same number of resources, but phase them out at a later date, right? So instead of hiring them 6 months early, say, hey, hire them 6 months later. That way you can balance your inventory without adding, additional money on getting another crew. So this kind of gave us very kind of interesting insights into how to solve the problems based on different uncertainty distributions across all the spectrums. Okay. Sure. So how did you balance meaningful and reliable information and the need for commitment to action? In other words, how did you convey this to an OR novice? Okay, so the way we approached this, I actually didn't even use the word OR when I presented this findings to leadership. All I really took was the valuation portion of the curve, which was my, that parabola that you saw, right? So all they had to see was, by deploying this optimization techniques, we were leaving, this amount of figure on the table, this amount of portfolio value on the table, by not adding more crews, right? So my technique was not to use technical terms in OR, right, but to show them the value proposition behind using optimization techniques. So that was one way to communicate things to them, especially to a non-OR audience, right? Because I've always found that the more technical jargon you tend to use, the more easily you lose them, from the true context of the entire conversation.
So I think we'll move to close now, just because we have the next session right in here. But
Okay.
and then, sir, there are some other good questions on here. So if you can maybe catch these guys, I'm not sure they're running right away afterwards. But thank you very much. Round of applause for Bobby and Bill.